This video is about optimization and finding the greatest and least values. So we're deciding to sell some computers in our spare time after school, and we're going to have two variables. Lowercase p will be the profit we make each week, and x is the number of computers that we'll sell each week. Okay, we'll note that we have a domain here that x needs to be between 0 and 20. I obviously can't make and sell any negative number of computers, but I'm also a school student, so I don't have unlimited time to be making these computers, so maximum I can make is 20 without affecting my grades. From my friend's experience, I know that my weekly profit will vary according to the following formula. So we've taken some data, found a line of best fit, and this formula describes how much profit we'll make for selling X computers. So the question is, how many computers should you sell weekly so that your maximum profit occurs? Okay, I know I'm trying to find a maximum point, okay, or I could, in other problems, optimization problems, be trying to find a minimum point. Okay, I know that in both of these 2 points, and indeed in my points of inflection, okay, the thing in common is that at that point the derivative is 0. Okay, so I need to find my stationary or turning points of this function. And we know they're going to occur when the derivative is 0 at p dash of x equals 0, since I'm using function notation. Okay, so first of all, I'm going to need to find what the derivative of x is. Okay, looking at this function, a third x cubed, multiply a third by 3 gives me 1, x, and reduce the power by 1. Okay, it was cubed, goes to squared. Okay, next term, minus 10 times 2 is minus 20, x to the power, reduce that power by 1. Okay, the power is now 1. I don't need to write that power. Third term, 96x. Okay, a linear term, which means I'll just write down the 96. And the last term is a linear, a constant term. When I differentiate a constant term, I get 0. So this is my derivative. Now I'm trying to find stationary points, so I'll set p dash of x equal to 0. And I'm looking for the x values which will satisfy this equation. I just need to relax and do some factorization. Okay, two things that multiply to x squared, all good. Now I'm thinking here of two numbers that will multiply to give 96, and when I multiply across the crosses, add to give minus 20. Okay, I know that both numbers need to be negative. How am I going to get 96? Okay, I think it's something to do with my 12 times tables. Okay, I'll have 12 times, I believe, 8. Does that work? 8 times 12, 80, and 16, 96. Sounds good. What I need to get a negative 20 in the middle, so both of these need to be negative. When I multiply across the crosses, I have minus 12x and minus 8x, giving me the minus 20 that I was after. Okay, so this is going to factorize to x minus 12, x minus 8, okay, equals 0. From here, I can use the Null Factor Law, which will tell me, since these two factors are multiplying to equal 0, either this factor is 0 or this factor is 0. Okay, so I end up getting two potential maximums, some sort of turning point that occur at x equals 12 and at x equals 8. Okay, I need to find what the profit is at these 2 points before I classify the turning points. Okay, so I'm going to sub x equals 12 and x equals 8 into my original formula, which is p of x is a third x cubed minus 10x squared plus 96x minus 150. Okay, to find the y, the p coordinates. So all I know at the moment is that at 8 and at 12 there's a turning point somewhere. Okay, I need to know the p coordinate so that I can place these 2 points, I guess, mentally on a set of axes. Okay, so I'll do this. I'll find what P of 12 is by substituting it in, and find also what P of 8 is. With magic of television, I've done this. So I know that I have stationary points. I'm not sure if they're maximums or minimums at all. Okay, but I know that the 2 points are 12, 138 and 8, 148.66. Okay, I don't know whether these are minimums or maximums, so I'll need to classify these two. So I'm going to classify them using the first derivative test. If you know the second derivative test, you can do that as well. So what I'm looking at is making a little table and looking around these turning points. So around where 8 is and around where 12 is, okay, and just looking at what the slope of these 2 points, slope around the 2 points are. So I know that the slope at 8 is 0 and the slope at 12 is 0. So both of these are going to be flat. I just want to investigate at either side. So I'm going to substitute in, say, 10, say 6, and say 14, okay, into my slope formula. So all of these substitutions, for example, in here will be P dash of 14. What's the slope at x equals 14? Which would be 14 squared minus 20 times 14 plus 96, okay, from my derivative. So I'll do that for all of these points in the table. So I've done all this. I've found the slopes at all of those points by substituting it into the derivative. And now I can draw my slope diagram. So 12 is a positive slope, 0 is flat, 4 is negative. So I know that 8, 148.66, okay, is a maximum. And then looking at the next point, 10 is a negative slope, 12 is flat, 0 is flat, and 12 is a positive slope. So I know that 12, 138 is a minimum. So you'll notice that I've left the gap between these two things because, and I said that it's a maximum, not necessarily the maximum, because what these points could be is they could just be local maximums. So they could just be a point where in the neighborhood around here, it's the smallest point in that little region. But there could be a point which is smaller than it overall. Same thing here. We could have a local, this 148.66 could be a local maximum when there's actually a bigger value out there. So at the moment, all I'm going to do is call these local maximums and local minimums, because I'm not sure whether they're actually the global maximum. If we look back to our problem, we'll recall that we have a domain here, that the number of computers we can make is also between 0 and 20. So to find the greatest and least value, or in this case, we're just after what's the maximum amount of profit we can make, I need to make a little table to find the greatest or least value. In this case, I'm after the greatest value, but I'll call it the greatest and least value table. I'm looking at a few points. I'm looking at the endpoints, so 0 and 20, and I'm also looking at any turning points in between, so 8 and 12. Okay, and at all these points, I'm looking at what's the profit for that number of computers. I've already substituted in for 8 and 12. So all I'm really doing is just checking these endpoints to see they're not bigger than the local min and the local max. Okay, so I'll substitute these 2 points in using my original function. Okay, so if I substitute 0 in here, P of 0 will be negative 150. You might think, how can I get negative 150 if I'm selling things and making profits? Well, 150 could be marketing fees, and you've sold no computers, so you still have to pay those marketing fees. Okay, and in here I'll be looking at whatever P of 20 is. Okay, so a third, 20 cubed plus 96 times 20 minus 150. Sub that into calculator. So I've substituted all of these points into my formula, and I've found that actually making 20 computers would make me $436.66. So I go back to the question, how many computers should you sell for a weekly or optimal profit? I would say I will sell 20 computers for a maximum profit of $436.66. Okay, so the real purpose of this lesson, and indeed the purpose of this last table, is that this is what the graph looks like. You could have graphed it on your calculator before doing the problem. That local maximum we found was about here. Okay, we also found a local minimum here where it turned around again. If we just solve this without considering our domain, which was between 0 and 20, we would have just stuck with this level of profit. However, evaluating the function value at 20, okay, found us that indeed we should be making 20 computers for our $436.66 profit. Okay, so just revising the general strategy here. If I'm ever solving an optimization problem, I'll first find and classify the stationary points of the problem. Okay, find where the local minimums and local maximums are. Okay, and then evaluate the function at the endpoints of the domain and at any stationary points. Okay, which also serves as a bit of a double check around here to make sure that I haven't accidentally classified my max as my min. All right.